Hi students, my name is Preba and I'm a teacher teaching science for 20 years. In this channel, you are going to learn the secrets to the theory and to understand the magnetic effect of a current carrying conductor, part 2. When you subscribe to my channel, you're going to learn more videos about electromagnet and you'll get great confidence to answer science questions. In this lesson, we will learn in detail the factors that affects the strength of electromagnet. Besides that, we also will be learning applications of electromagnets such as electric bell, telephone earpiece, circuit breaker, and lifting magnet. Every single week, I will upload one video. If this is the first time you are visiting my channel, make sure you hit the subscribe button below and click on the bell and turn on the notification. Hello students, welcome to my Science Buddy channel. My name is R.Prebasubah and we will be studying part 2 today. It consists of factors that affect the strength of an electromagnet and application. Let's start off by learning the factors that affect the strength of magnetic field. Here we can observe two different experiments. Every component is the same except the batteries. On the left, the illustration shows one battery attached, while on the right hand side we have 5 batteries attached. Now let's look at manipulated variable, responding variable, and constant variable. The answers are here. Therefore, the manipulated variable for these two experiments is value of current. The responding variable here is number of paper clips attached. I would like to highlight here that the number of steel paper clips attached indicates the strength of the electromagnet. And the constant variable here is number of turns of wire and type and material of wire. After the experiment, we have recorded the number of steel pins attracted to the lower end of iron rod. Now, I would like to place the answer. So for the first experiment, I'm going to put the number of paper clips attached, that is 2. And for the second experiment here, somewhere around 10 number of paper clips that is attracted in here. Now, we realize a connection between the current flowing through the solenoid and the strength of electromagnet. Now, I'm going to place a note in here. Therefore, in order for us to see the connection between the current and the strength of the magnetic field, at the same time, I'm going to place the magnetic field lines that is created around the solenoid. This illustration in here. So what we understand here, so higher the current flow, higher the strength of electromagnet. This can be illustrated with these magnetic field lines. So I can conclude in here, higher the current, the more magnetic field lines that is created, therefore stronger electromagnet is produced. The next factor is number of turns of wire. Here we can observe two different experiments. Every component is the same except the number of turns of wire. On the left, the illustration shows less number of turns, around 5 coils of wire, while on the right hand side we have around 12 coils of wire. Now let's look at the manipulated variable, responding variable, and constant variable. The manipulated variable for this two experiment is number of turns of wire. The responding variable here is number of paper clips attached. Here, the number of steel paper clips attached indicates the strength of the electromagnet. And the constant variable here is value of the current or the type of material of wire. After the experiment, we've recorded the number of steel pins attracted to the lower end of the iron rod. So from the first diagram, the number of paper clips attached is somewhere 2 paper clips that is attached to the end of the solenoid, while in the second experiment it's somewhere around 12 paper clips that is attached to the end of the solenoid. So what can we understand from here is the more the number of turns, therefore more number of paper clips that is attached, while less number of turns, less number of paper clips. So here we realize a connection between the strength of electromagnet with number of turns of solenoid. The more the wire is coiled around, the higher the strength of electromagnet. So I'm going to put the magnetic field lines that is created around these coils. So in this first diagram we can see the magnetic field lines that is created is more, while in this picture, in this illustration, we can see less magnetic field lines. And I would like to put a note here which gives us a better understanding between the number of turns on this and the strength of magnetic field lines. So this can be illustrated with these magnetic field lines, the relationship between the number of turns of wires and the magnetic. So in conclusion, the more the coil wire in solenoid, the more magnetic field lines created, therefore stronger electromagnet is produced. The next factor is type of core used in the solenoid. Here we can observe 3 different types of core. They are nickel, steel and soft iron core. Did you realize I only used materials such as nickel, steel and iron? This is because they are ferromagnetic materials that can easily magnetize. Materials such as copper, aluminium and lead are non-ferromagnetic materials. Let's conduct an experiment using different cores. The manipulated variable, responding variable and constant variable. Manipulated variable for this experiment is type of material of core. The responding variable here is the number of paper clips attracted. The number of steel paper clips attracted indicates the strength of the electromagnet. The constant variable here is the current value and the type of material of wire. First, we'll try nickel core. When I place the nickel core in here, I realize the number of paper clips that is attracted is 3 paper clips. Next, we'll try with steel core. What I'll do, I'll place this at this position to illustrate that the nickel core attracts 3 paper clips. Next, I will place steel core. When I use steel core, I realize I attract 4 paper clips in here. Next, I will use soft iron core. So what I'll do, I'll remove this core and place it here for us to see and compare the cores. Next, I will place soft iron core in here. But when I use soft iron core, I realize I attract somewhere around 10 paper clips. So I will remove this soft iron core and place it here. If we compare based on the number of paper clips attracted, the soft iron core seems to attract more. If we were to see nickel core, it only attracts 3 paper clips. Steel core, it attracts 4. But the best of all is soft iron core, which attracts 10 paper clips. Therefore, we realize a soft iron core is the best metal to be used as a core. Soft iron core is used in electromagnet devices because its magnetic permeability is high and is easily magnetized and demagnetized fast. While the advantages, so I'll just put the notes here. Now, as you can see, the advantages of using soft iron core in electromagnet, because it is able to concentrate the magnetic field lines through it and produces stronger electromagnet field, as you can see in this illustration. Next, let's summarize all the factors. Finally, we can summarize the factors affecting magnetic field of an electromagnet. They are the size of electric current, where the higher the current, the stronger the field. Besides that, number of turns, where the greater the number of turns, the stronger the magnet. And finally, the use of soft iron core, where the magnetic field will be more concentrated. Next, we will see some applications using electromagnets, and we'll start with electric bells. Now, we are going to learn how the electric bell works. An electric bell consists of 2 electromagnets with solenoids moving in direction opposite to each other and soft iron armature. When a bell button is pressed, a complete circuit is created, makes the current flow. Now, let me go back to the diagram and explain to you how the current flows. When the bell button is pressed, that makes the switch on. Therefore, the battery produces the current flow, which completes the circuit, and the current flows in this direction. When it comes here, it passes through the solenoid, which consists of soft iron core inside, and the second solenoid, and it passes through the soft iron armature, the metal piece in here, and it passes through this contact point in here, which is vital for you to understand, because this is the one that makes on and off, and it goes back to the battery. So, when the current passes through the 2 electromagnets with solenoid wound, it creates magnetic field around it. So I'm going to put a magnetic field lines here, so it gives you an idea what happens when the presence of current flow. So due to this magnetic field lines, what happens? This creates a magnetic field effect on the soft iron armature. The soft armature is attracted to the electromagnet. So, this soft iron armature will be attracted to these magnetic field lines and the magnetism that is created by this, and therefore this thing will be glided and attracted, and this is what happens. Can you see that this actually will hit the gong, which produces the sound? So the soft iron armature will be attracted. But did you realize that there is this point in here with this point and this contact is no more? This makes the current get disconnected. So I'm going to place note number 3 in here to actually make you understand that the soft iron armature is attracted. Now, and followed by note number 4, whereby it shows that as soon as the hammer moves towards the gong, the circuit is broken. So the electromagnet loses its magnetism when there is no current flow. So as there is no contact anymore, the electromagnet loses its magnetism. The striker or armature springs back to its original position. So let's go and see what happens. So I'm going to put note number 5. The electromagnet loses its magnetism, and note 6, where it pulls back it completes the circuit again. So again, when there is no more contact, there is no current flow, I'm going to remove this magnetism. It actually disappears. Therefore, the soft iron armature will return back by this spring effect, which makes it to go back to its original position, and this actually completes the circuit again, where the current will flow back into the circuit, where it comes out from the battery, and as it passes through the solenoid and passing through the soft iron armature, the current flows go back again. And due to this current flow, magnetism is created. This pulls this soft iron armature back into this position, which hits the gong. Due to the disconnection that happens, the magnetic field lines disappear, and since there is no magnetic effect in here, therefore the soft iron armature will return back. Now can you see it happens again and again? Okay, it's a continuous process. So this process repeats as long as the user presses the switch and the striker hits the gong continuously, producing a loud sound. Next, we will see another applications using electromagnet, that is telephone earpiece. What you can see is a telephone earpiece. It consists of permanent magnet, soft iron core, and one alloy diaphragm. Inside a telephone earpiece, 2 electromagnets are fixed on a permanent magnet. When a current of varying magnitude passes through the solenoid, the strength of the electromagnet changes. So I'm going to show you what happens when there is a current flow. In the soft iron core, electromagnet is created. Due to this magnetism that is created, the alloy diaphragm will be attracted towards the soft iron core. The electromagnet varies in magnetic strength according to the varying current. Due to soft iron core, the diaphragm is pulled by the electromagnet with a changing force. Hence, the diaphragm vibrates with a sound of similar frequency as received by the earpiece is produced. Next, we will see another application using electromagnets, that is circuit breaker. In normal condition, the current flows from the main supply to the household circuit by passing through the contact and the coiled wire. This coiled wire produces magnetic field lines that is enough to pull the soft iron armature to touch the contact point. Right? But when there is a huge current flow from the main supply, this is where things change. The strength of magnetic field of the electromagnet increases suddenly. As I'm putting this, at least you will understand what's going on. As the current increases, the strength of electromagnet increases. The soft iron armature is pulled towards the electromagnet. This results in the spring pulling apart the contacts. The circuit is broken and the current flow stops immediately. After repair has been made, the reset button is pushed to switch on the supply again. Next, we will see another application, that is electromagnetic crane. What you see here is an electromagnetic crane. It consists of soft iron core and thick cables carrying large current. Huge electromagnets are used in cranes to lift scrap metal. Opposite poles on the surface will produce stronger magnetic field. When the current of electromagnet is switched on, the soft iron core is magnetized to become a very powerful magnet. The huge electromagnet picks up iron and steel scraps and moves them around. When they have reached the destination, the current is switched off and the soft iron core is demagnetized. The scrap will drop to the desired location, and what we see here, the advantage of this electromagnet cranes are, it only attracts ferromagnetic materials such as iron, steel, cobalt and nickel. It can separate ferromagnetic from non-ferromagnetic waste such as copper, aluminium and lead. And it can lift heavy loads of iron and steel bars which are difficult to handle otherwise. Well, we have finally come to an end of part 2. In my next lesson, in part 3, we will be learning force acting on a current carrying conductor in a magnetic field, the turning effect of current carrying coil in a magnetic field, and an introduction to direct current motor. If you like my video, please don't forget to subscribe, comment and like. Thank you for watching and have a pleasant day ahead.